Everyone, welcome to the CE111 lecture for September 7th. As I said, I'm going to be using a new software that I haven't used before for recording a lecture, so I'm hoping things will go smoothly, but I haven't taken any trainings by Khan Academy or somebody else who's much better at this, so maybe a little rough at times, but we'll hope for the best. Okay, so today we are going to be starting the material from Chapter 3. Oh boy, that looks great. And Chapter 3 deals with transformation processes. And there are all different kinds of transformation processes that are super important in environmental engineering. The types of transformations that we will be talking about in this chapter include phase transitions, which we will be talking about today, and also Friday. And then we will move on to acid-base reactions, and then redox reactions, and then we'll come back to kinetics. We're going to be working on this material for the next 3 weeks. So your reading assignment this week is pages 76 to 82 and pages 92 to 106. So let's go ahead and get started. I'm trying to adjust my trackpad a little bit here. Okay, anyway, it's gonna work. Okay, so here we go. Section 3A, phase transitions. So with phase transitions, we're talking about transformations between solid and liquid and gaseous states. And so first, let's just go over some basic stuff about chemical reactions and equilibrium. So if we have an elementary reaction means that the reactants that are participating in the reaction react with each other as shown by the stoichiometry of the reaction. So let's say we have A moles of reactant A reacting with B moles of reactant B, and that goes on to form C moles of reactant C and D moles of reactant D. So there is a forward reaction that can be represented by a forward reaction state, and then all reactions, at least in theory, also can occur in the reverse direction, so that is represented by the reaction rate constant K sub R. So if this is an elementary reaction, it means that the reactant A and reactant B have to have a collision in order for that reaction to occur. And so from that information, we know that the rate of the forward reaction is proportional to the concentration of each of the reactants raised to their stoichiometric participation in the reaction. Oh geez. See if I can remember how to erase. Yay, that worked. Okay, so and the proportionality constant is the rate constant. So we have, that's supposed to be a little k sub f times the activity of our reactant A raised to the power A times the activity of our reactant B raised to the B power. Now, in chemistry, you should have learned about activities. So activity is a way of representing the activity of any species that's participating in a reaction. So A equals the activity. And for species that are represented in dilute concentrations and aqueous in solutions, the activity is equal to its mass concentration. And this assumption that it's equal to the concentration for dilute species or for ideal species applies to many impurities in water and air. There are some conditions under which it doesn't apply, so we've already talked about them. Last lecture we talked about the effect of ionic strength on the activity of chemical species, and I mentioned that for ions, if they are present in a solution with high ionic strength, then the presence of all the other ions actually reduces their chemical activity, because the counter ion, say you're talking about the activity of a positively charged species, then a bunch of negatively charged species will surround that cation, and so that actually decreases its ability to have a bimolecular reaction, so to have a collision with another species and react with it. So those conditions do occur, but for dilute species, that the decrease in activity is small and insignificant for our purposes. But I encourage you to look at Appendix E, which has subsections on a bunch of useful material to review coming on the thermodynamics of chemical reactions, and Section 1 is a review of activities. So back to our reaction rate expression over here, we can simply replace the activities with their mass concentrations. And the convention is to use molar concentrations here. Okay, so we have an expression now for the forward rate. The reverse rate constant, an expression for the reaction rate in the reverse direction can be written as well. So now we have the, oh gosh, I got the rate constant subscript wrong as well. Okay, that should be an R. For the reverse rate constant, so now we have the activity of species C raised to the C power times the activity of species D raised to the D power, but we can assume that the activities can be replaced by their mass concentrations. So we now have that the reverse reaction rate is equal to K sub R times the molar concentration of C raised to the C power times the molar concentration of D raised to the D power. I just realized that I said something a little bit incorrect. So if A and B are equal to 1, then we have a bimolecular reaction. We have one molecule of A reacting with one molecule of B in order for reaction to occur. But if the stoichiometry is different, so if A is equal to 2, then we have two molecules of A reacting with B. And those kind of reactions are actually very uncommon, because it's so unlikely that a collision occurs between three chemical species. But they can exist. So we're going to write this as a general reaction. Okay, so we are often interested in equilibrium, and in characterizing phase transitions, we're often interested in expressing the equilibrium condition. So at equilibrium, we can assume that the rate of the forward reaction is equal to the rate of the reverse reaction. Therefore, RF is equal to RR. And so we can then substitute in from above K sub F times A to the A times B to the B is equal to K sub R and we can then introduce a new variable, capital K, and capital K is the equilibrium constant, and it is defined as little k sub f or over little k sub r, so we just solve, it's supposed to be equal here, if we just solve the equation above for k sub f over k sub r, we have the concentrations of the products raised to their stoichiometric coefficients on the top times the product of the reactants on the bottom. And this is a relationship that you are familiar with from basic chemistry classes. And just a reminder that the mass concentrations in each of these expressions, so all of these concentrations represent the equilibrium concentrations, are at equilibrium. And K is the equilibrium constant. And even though it's called a constant, it's important to note that it does vary with temperature, because there are all different kinds of ways in which the temperature can affect the reactions that are being described. Okay, so let's move on now to actually describing some different phase transition reactions. So the first one we will start with is phase partitioning between a pure liquid and a pure gas. It is so much harder to write on this tablet than on the board. So thank you for your patience with my bad handwriting. So the equilibrium relationship that we will define here is called the vapor pressure. And it is represented by capital P sub I for the species of interest with a 0 up at the top, or I guess it's not a 0, a naught, I think we call that, indicating that that's at equilibrium. So this describes hold on just a second, let me check my notes on one thing. I wrote something a little wrong here. So this phase partitioning between a pure liquid and a gas specifically refers to the equilibrium relationship that's described by the vapor pressure. Okay, I'm going to be talking about different types of phase partitioning between other states of matter as well. Okay, so the vapor pressure describes the equilibrium between the pure compound which is the liquid, and the gas in this case is air. So in this case we have our pure compound that is a liquid, and through evaporation it can enter the gas phase, and then through condensation it can return to the liquid phase. So the equilibrium relationship is, as I said, the vapor pressure, and that describes the ratio between the partial pressure of species A in the gas phase and the activity of the species A in the liquid phase, but the activity of compounds in their pure state is equal to 1. So we can rewrite this relationship where this naught indicates that we're talking about the equilibrium condition as P sub I, P naught sub I at any temperature T. We're going to explicitly recognize that this constant is a function of temperature, is just equal to the vapor pressure at that temperature T, the equilibrium vapor pressure. Okay, so the equilibrium partial pressure is a constant, which is known as the vapor pressure. So to illustrate this concept, let's go ahead and do one example. Imagine that we have a container that in the pressure in the container is 1 atmosphere. The temperature is 25 degrees Celsius. And to that container, we add a mass of benzene. Okay, benzene is a petroleum compound, a 6-carbon ring. We add a mass of 1 mole. And the question is, what is the distribution of benzene between the gas and liquid phase? So in order to answer that question, we need some additional information. We need to know the vapor pressure of benzene. And your book provides a table of vapor pressures for some common compounds. So in table 3.b.1, we can look up the vapor pressure for benzene at 25 degrees C is equal to 12,800 pascals. Now the conversion from pascals to atmospheres is in one of the tables on the front flap of your book. So I'm going to go ahead and give you that, do that conversion for you. So that's equal to 0.127 atmospheres. So there are 2 possibilities, although you can already see from the vapor pressure I've given you that only one of them is really reasonable. But the 2 possibilities are, the first one is that all of the benzene exists in the gas phase. And we can see that because the partial pressure is, well, actually, I guess we can't see it yet. Okay, so the first possibility is that all of the benzene is in the gas phase. So if the concentration of benzene stays below, or the partial pressure stays below 0.127 atmospheres, then all the benzene will stay in the gas phase. The second possibility is that some of the benzene is present as a pure liquid. So let's investigate the first possibility. So the first one, as we said, is that all of the benzene is in the gas phase. So to calculate that, we are going to use our knowledge about the we're going to calculate what the partial pressure of benzene is. Using the information that was given in the problem. So we can calculate the mole fraction. Gosh, sorry, that was so hard to read. The mole fraction of benzene. So the mole fraction of benzene is the moles of benzene per the moles of air. So we know that we added 1 mole per cubic meter of benzene to that container. And that container is also filled with air. And if you use the ideal gas law, you can calculate that the molar concentration of air molecules at 1 atmosphere of standard atmospheric composition is 40.9 moles per cubic meter. That's for the air. So we find that the mole fraction of benzene is 0.024. Therefore, the partial pressure of benzene is 0.024 times 1 atmosphere. So it's 0.024 atmospheres. So then we just compare this concentration to the vapor pressure, and we see that the partial pressure of benzene is less than the vapor pressure at that temperature. Therefore, all of the benzene is in the gas phase. So that was a good place to start. A good assumption to start with for this problem. But just for the sake of doing this example, let's explore the other possibility. So the other possibility was that some of the benzene would be present as a pure liquid. And so I'll change the question slightly and say, how many moles would we need to add in order for that to occur? So we would need to exceed the vapor pressure. And so if we plug the vapor pressure in, we can calculate how many moles would be needed in order to achieve that partial pressure of benzene. Okay, so N equals PV over RT, and we're going to plug in here 0.127 atmospheres. We have 1 cubic meter. And our ideal gas constant times the temperature, and we get 5.2 moles. So we would need to add not 1 mole, but 5.2 moles in order for benzene to reach its vapor pressure, and then we would need to exceed that in order for benzene to exist in its pure liquid state once the system comes to equilibrium. So we can summarize these conditions in a graph very nicely. So if this is the partial pressure of benzene, and here is the vapor pressure, then on the y-axis we're going to represent the number of moles of benzene that are added, and this is for our 1 cubic meter container. And so the partial pressure of benzene will increase linearly. See my nice straight line there, until we reach the value of 5.2 moles. Right? Because through the ideal gas law, the partial pressure and the moles are just directly proportional. Then once we reach that vapor pressure, then there can't be any more benzene in the gas phase at equilibrium, and so the rest of the benzene that we add has to be present in as a pure liquid. So we could represent that. This line here would be the mass of pure benzene. Mass of benzene present as a pure liquid. Neat, right? Why is this important for environmental engineering? Well, it turns out that we actually use a lot of chemical compounds as pure liquids. So for example, we often transport compounds like petroleum compounds or different types of solvents in tanker trucks. And once in a while, one of those will spill. Or another example would be we often store those compounds in underground storage tanks, and sometimes those storage tanks leak. And so the pure compound could be present in the environment, and we're interested in finding out what the gas phase concentration is, or vice versa, once that comes to equilibrium. We could also be interested in finding out what the gas phase concentration is inside of the container that's being used to transport the material. Now there's a special application of the vapor pressure concept to the water itself, the fluid itself, which can also evaporate. Whoops, I meant to write special case. So there's a special case, and that is when we're interested in evaporation or condensation of the water itself. And so there's a special relationship that will sound familiar to you. There's a term called the relative humidity, or the RH. And that has its own unique definition. It is defined as the partial pressure of H2 that exists divided by the partial pressure of H2O at equilibrium for that particular temperature. And then it's represented as a percent, so we're going to multiply by 100. Okay, so this right here is the saturation vapor pressure. Okay, so the units for this are percent. So this is another relationship that you need to be familiar with. This relationship, as with the others, is quite sensitive to temperature, and that is illustrated nicely in figure 3b1 in your textbook. And so that relationship looks something like this. The equilibrium partial pressure versus temperature, and it increases quite dramatically. And there's a value that you'll be familiar with at a total pressure of 1 atmosphere and a temperature of 100 degrees, something special happens. At sea level, where the pressure is 1 atmosphere, if the temperature of the water reaches 100 degrees C, it boils, and that's because its vapor pressure has been exceeded. And then, as you know, if you're at a lower pressure, so as you go up in elevation, then water boils at a lower temperature. Okay, so I'm illustrating this relationship here. So at sea level, where the pressure equals 1 atmosphere, water boils at 100 degrees C. Because the partial pressure of water then equals the atmospheric pressure. Neat. So the next thing we're going to talk about is aqueous solubility. So this is the solubility of things in water. And we're going to start off talking about the solubility of pure liquids in water. So there's a special term that you need to be familiar with. So in the case of pure liquids existing in equilibrium with water, we're only talking about liquids that do not dissolve completely in water. So we're talking about there being 2 liquid phases. One liquid is water, and the other liquid is the other liquid that doesn't dissolve in water. And so when that exists, it's called a non-aqueous phase liquid, or a NAPL. And NAPLs are kind of analogous to the condition we were just talking about with, let's say we have a spill of benzene, and some of that benzene can volatilize into the gas phase. Well, if water is also present, then some of that benzene could dissolve into the water as well. So now we're talking about the transition of that liquid to the aqueous phase, which is has the subscript AQ, the aqueous phase, meaning it's some of that compound A is dissolved in the water. So if we look at the equilibrium constant that would describe that relationship, we're going to call that the water solubility equilibrium constant. Okay, and that's going to equal the activity of the compound at equilibrium in the aqueous phase, so that's supposed to be AQ, divided by the activity of the compound in the liquid phase. So like we've said previously, the activity can be or is equal to just the mass concentration for dilute species, and for pure compounds the activity is just equal to 1. So that allows us to restate this relationship for the equilibrium condition. So we can say that the concentration of the species at the stated temperature is just equal to the water solubility at that temperature. And that is a constant at that particular temperature. So this condition only exists if that compound is also present as a pure liquid. So if a napple is present and is in contact with water and the system is at equilibrium, then the concentration of that compound in the aqueous phase will equal the water solubility. And it's kind of helpful to think about what that means if the system is not at equilibrium. So if the system is not at equilibrium, and the concentration of the species is greater than the water solubility constant, then that means that system is supersaturated with respect to the compound, and so some of the compound will leave the aqueous phase and a napple will form. And the other condition could be that if in your system you find that the concentration of the compound is lower than the aqueous solubility, but it's not at equilibrium, and if there's a napple present, then some of that napple will dissolve until equilibrium is reached. So that's extremely helpful for understanding the fate of compounds in the environment. Is if a compound is spilled and so the napple is present, the compound will dissolve into the water until the water solubility limit is reached. There's another interesting property of pure compounds that are not soluble or that don't mix with water, and that is that if the density of the substance is less than that of water, then it actually floats. In other words, like an oil. And benzene also has a lower density than water, so it will float. And in that case, it's called a L-napple, or a light non-aqueous phase liquid. And then if the opposite is true, that if the density is greater than water, then the pure liquid will sink and accumulate below the water. And there are a bunch of compounds that fall into that category, like chloroform, carbon tetrachloride, and those are called dense non-aqueous phase liquids, or D-napples. So let's do another example. Let's say we have, again, our 1 cubic meter container, but now it's filled with water and there's no air. But it still has a volume of 1 cubic meter. and it still contains 1 mole of benzene. So now we're interested in knowing, is there a NAPL present? In this case, it would be an L-NAPL. So your book also provides you with a table listing the water solubilities of some common compounds. So you can look up in table 3B3 and find that the water solubility for benzene let's see, it's for 20 degrees C unless otherwise specified, and that the water solubility is a little bit less sensitive to temperature. So, and the value is 1,780 milligrams per liter. So in this example, just like in the previous one, there are two possibilities. One is that that entire mole of benzene is dissolved in the water, and the other possibility is that a NAPL is present. So we can explore the first possibility and assume that it's all dissolved. So if we calculate then what the concentration would be, we have 1 mole of benzene in a cubic meter of water. So we just need to do some conversions here. So we'll convert cubic meters to liters and then multiply by the molecular weight of benzene. So the molecular weight is 78 grams per mole, and convert to milligrams, and we get 78 milligrams per liter. So then we can just compare that with the water solubility, which is much, much greater. So we conclude that no NAPL is present. Now again, for the sake of exploring all the possibilities, we could look at under what conditions would there be a NAPL present. And so if instead in the previous equation we plug in the water solubility here and then solve for the number of moles, we would find out that you need to add 22.8 moles would need to be added for NAPL to be present. Or actually that's more than 22.8 moles would need to be added for a NAPL to form. All right. The next type of solubility we're going to look at is the solubility of gases in water. So now we're talking about the phase transition of a compound present in the gaseous phase and becoming dissolved in the water, so from the gas phase to the aqueous phase. And in this case, the solubility coefficient can be represented as the equilibrium of the species in the aqueous phase, the activity of that species in the aqueous phase divided by the activity of that species in the gas phase. And so again, we can represent the aqueous activity as the concentration and the gas phase concentration as the partial pressure. So the equilibrium relationship is known as Henry's law and is often represented in this way. KH is equal to the concentration of the species in aqueous phase divided by the partial pressure. And when written this way, the units are in molar concentration divided by atmospheres. But it's a frustrating thing about Henry's law is that it can be written using lots of different conventions. So it can also, or it is also commonly represented with the definition just being the inverse. So, and the symbol for that when it's written in the inverse way is H sub G is the equilibrium constant, which is just equal to the inverse of K sub H. So it's really important that whenever you're talking about a Henry's law constant or a equilibrium constant describing the partitioning between a substance in the gas and the aqueous phases, you need to check the units. And these two forms are so common that the table in your book that provides you with some Henry's law constants, table 3.2, has the constant represented using both of these unit conventions. One of the most common applications of needing to understand the equilibrium concentration of a gas in water in environmental engineering is the solubility of oxygen in water. Wow, those axes are just so bad. Let's try again. A little better. So, the Henry's law constant is quite sensitive to temperature. It's supposed to be H comma oxygen. And so it decreases with temperature. And that matters a lot. So this is in your textbook, figure 3b2. And there's an example that I would like you to study, which is example 3b2 in your text. This relationship, or the fact that the Henry's constant decreases with temperature, is really significant in surface waters, because surface waters that are in equilibrium with the atmosphere have the maximum concentration of oxygen that they can hold. And a lot of aquatic species, in particular fish, are used to being in waters that are saturated with oxygen. They need a lot of oxygen in order to breathe underwater. As the temperature of water increases, the solubility decreases. And so the maximum amount of oxygen that that water can hold goes down. And so that can have a detrimental effect on fish species. So in addition, so if waters become warmer due to human activities, then there can be two effects on fish. One is that the temperature may get out of their ideal temperature range, but also the solubility of oxygen goes down, and so they may not be able to survive at those temperatures. Okay, we're going to cover one last concept, and that is the solubility of solids in water. Okay, so this is the phase partitioning between a solid and water. So in this case, it's the species that's going to react is a solid that's made up of a minimum of two different chemical species. And we're interested here in ionic solids that are going to dissolve in water. So I've been using the example sodium chloride. So this could be sodium and chloride. And that solid can dissolve in water. And it will form X moles of A and Y moles of B when it does so. And similarly, if that solid exceeds its solubility, or if those species exceed their solubility, then it can precipitate. So the equilibrium relationship, constant that we would write, is that the activity of A raised to the X power times the activity of B raised to the B power divided by the activity of the solid would give us our equilibrium relationship. Remember, so for these guys, we can substitute their concentrations, and because this is a pure solid, the activity is equal to 1. So we can represent this whole relationship by the solubility product. That's just the name of the equilibrium constant. And again, it is only a constant at a particular temperature. And so it is equal to the concentration of A raised to the X power times the concentration of B raised to the Y power. And I just realized that I wrote that wrong up here. So this should have been the activity of A raised to the X power, yikes, the activity of A, activity of B. So this is called the solubility product. There is a table in your book with the solubility products for some common compounds of relevance to environmental engineering. So see table 3B4 in your textbook, and also there's a nice example that I would like you to read through, 3B4. All right, we'll stop with that for today, and I will see you in person on Friday.